Welcome to Process number 84, and today we're looking at de-icing wings and ice regulation and their effects on flight dynamics and aircraft aerodynamics and wing aerodynamics. So to do that, we're going to look at the paper called the optimization method of wing ice shape regulation based on flight dynamic characteristics. And this is important because when you're flying around up at 10, 20, 30, 40,000 feet or higher, it's very cold, but you still have some humidity, some water in the air. And over time, that can form ice on the leading edges and other parts of the aircraft. But mainly, we're going to be looking at leading edges today. And then that changes the aerodynamic performance because then the leading edge changes shape, the airfoil profile changes shape. And as we know, airfoil profiles affect the aerodynamics of the airfoil. So let's get started here. So ice on an aircraft, the wing, changes the aerodynamic shape, causing damage to the flight mechanical steering system as well, potentially. In severe cases, it may even lead to losing control of the aircraft. In recent years, many serious flight accidents have been caused by icing. For example, the Russian Saratov airliner AN-148 got the wrong speed information from pilots due to icing on the airspeed tubes, and it eventually crashed in 2018. So that's a major danger because for those of you who aren't familiar with aircraft wings, next time you go on an aircraft or an airplane or you're just in the airport or whatever, look closely at the wings and you'll see all these little tubes coming out at different points. And mainly at the front, there are also some at the back. They're called strakes. They're a little bit different usually. The ones at the front pointing up, they are there, even around the cockpit actually. They're there to provide the pilots with information. So based on airspeed and humidity, density and altitude and all that kind of stuff. So if they ice, then you get wrong information, then that means that you can't really control the plane as well because the information you're getting is wrong. So another situation was General Aviation B-10GD. That model precipitation enhancer crashed because of the propeller icing in 2021, and some crew members unfortunately were killed. And that's quite surprising considering that the propeller is moving around so quickly. But even that shows that even the propellers are susceptible to icing, and it's not just airfoils. Research has shown that UAVs were more sensitive to ice conditions than larger, faster manned aircraft, and aircraft icing was one of the major hazards for airplane operation during takeoff, climbing missions at low temperature regions. So that makes sense because when an airplane is cruising around, that's actually that's usually the safest part of its operation. Landing and takeoff are the two major risk areas. And if you have the icing going on, then you're messing with aerodynamics during landing and takeoff, and that is much more dangerous than a cruise, generally speaking. So the aerodynamic characteristics of the aircraft are greatly affected by ice accretion problems. So accretion just means when the ice builds up. Innovative de-icing techniques are urgently needed because of that. So at present, two common de-icing techniques are heating and vibration. So compared with vibration, heating de-icing systems are mostly used for small components such as airspeed tubes, and they have a low response and low thermal efficiency. That's why you can use these. Meanwhile, the low reliability of vibration de-icing systems would greatly damage the original aerodynamic shape of the aircraft and reduce the aerodynamic performance of the wing. It's pretty cool how you think like if you just vibrate something, the ice will eventually break off, which makes sense because if you have a structure which can vibrate, it not only means that the inertia is going to shake the ice off, it also means that the structure itself is going to bend a little bit, and ice doesn't have the same flex properties or the same stiffness as any other material. Every material has a different stiffness. So if you bend something a little bit more than another material, you're going to start to break one material off the other, and that's a good idea. Although, as I mentioned here, that's not potentially good for aircraft aerodynamics or longevity. The de-icing technology of plasma, though, has the advantages of low power consumption, quick responses, and simple geometries. Experiments have shown that its total efficiency is better than under certain conditions. So plasma actuators, what they do is you have two electrodes which are divided by Kapton tape usually. And Kapton tape is just a type of, it's called a dielectric material, and this just allows the electricity to flow in the right way to create plasma. And plasma is just when you have a gas of some sort and you strip all the outer electrons off the shell, and then you're left with this positively charged nucleus with some of the shell still around it, depending on what a gas you have. But that's plasma, and that's usually very hot, and that's what they use here. And you can produce plasma very cheaply in terms of not only financially but also in terms of energy wise. You can use like literally a battery pack to do it very easily. It doesn't require high power at all, depending on how much you want, of course, but you can do it with very low power. So a researcher found that actuators in the streamwise laid out in the streamwise direction, so the plasma generators, had a better de-icing effect than actuators in the spanwise layout. So that makes sense because if you have them in the streamwise direction, so it means that it's in the same direction as the free stream velocity. When you have more plasma in that direction, it means you can heat up that surface quite well, and the air flowing over it is going to flow the entire plasma tape. Whereas if you have it in the spanwise direction, only a small amount of the tape is going to see the one piece of air. So the air is going to flow over just a little bit, and it's not going to get nearly as much of the heat because it's not seeing as much plasma. So that makes sense. So these results showed that plasma actuators in the streamwise layout not only prevented ice accretion near the airfoil leading edge, but also allowed plasma-induced surface heating to further downward convect to prevent ice accretion near the airfoil's trailing edge, which I mentioned can occur as well. So that's good because the air is hotter. A team studied the influence of the thickness of the exposed electrode on the performance of the plasma actuators in the de-icing system, they found that the actuators with thicker exposed electrodes can induce higher average surface temperatures compared with a traditional actuator. So that's pretty cool. And they have a diagram here, figure 1, showing what it looks like. So they have let's say we have the leading edge of the wing. We have like a little cutout. Then over the top, we have this tape, and it's in like a reddish orange box on this figure. And then you have just a few strips going streamwise. And each one of these strips is the plasma actuator. And between these strips, you have a distance 4 centimeters. Here they have the heating elements, which are the plasma bits. They're 1 centimeter thick, or 1 centimeter wide. So you effectively have intermittent heating along the leading edge. And this is important because where the heating is, that's where the ice is going to melt away. Where the heating isn't, that's where the ice is going to accrete. Accrete. So figure 2 shows the process of the plasma ice shape regulation at different moments. So they want to see not just getting rid of ice in total, but seeing if you can just control the ice accretion and produce shapes which are not that detrimental. So they're still not getting rid of the entire ice, but you're going to make it a lot better instead of having ice over the entire leading edge. They say that overall, this paper mainly studied aerodynamic parameters under 2 kinds of regulation ice shapes based on wind tunnel experiments. 6 degrees of freedom flight dynamics models on the background aircraft are established. Simulations and comparisons of the trim characteristics, dynamic stabilities, and maneuverabilities are investigated. So I just want to talk a little bit more about this ice accretion regulation, because it actually fits into one flow control device that it reminds me of very strongly. So the way that the ice is forming is, like, imagine you have the leading edge and then just like little like patches of ice forming, and these are forming bumps. Then between the bumps, there's no ice. So you get like this wavy leading edge. And this reminds me of a flow control device called tubicles. And tubicles, I have actually a lot of experience in researching, and that's why it reminded me of them. And they're a passive flow control device, and they look very similar. They're just bumps on the leading edge. The main benefit of tubicles is that when you pitch them at non-0 degrees angle attacks, they start to produce leading edge vortices. So very similar to vortex generators. And these vortices then can delay stall, and that's one of them. That's their major benefit. They do have other benefits, such as reducing drag under certain conditions and increasing lift under certain conditions. But generally speaking, it's just the stall characteristics. So they delay stall and they soften stall. Those are the 2 major draws. And these bumps look very, very similar. Now, the difference here is that tubicles are usually investigated under high angles of attack. These are for low angles of attack. Now, yours truly investigated tubicles under low angles of attack as well. So, this sort of falls into my wheelhouse. And there is some benefits if you have the tubicles the right geometries. Now, I'm not going to go into tubicles too much because that's like a whole podcast series in itself, and I'd like to talk about it much more because I know a lot more about it. But I'm just drawing some similarities there between this kind of geometry and tubicles. So they say here that plasma ice shape regulation mainly uses the thermal effect of the actuator to cut the continuous ice into intermittent ice. So instead of you have an entire ice slab on the front, you cut it up, and in between these slabs you have the leading edge exposed. And then as shown in figure 2, which I mentioned earlier, they look like tubicles. The plasma actuators were arranged, the ice was removed where the plasma actuators were. Conversely, where the plasma actuators were not present, ice accretion was serious, and the width of the interval ice can be modulated by adjusting the arrangement of the plasma actuators. In other words, if you place more plasma actuators closer together, then you're going to get rid of more ice. If you place them further apart, you're going to have bigger patches of ice. So how do you select the optimal ice shape regulation parameter, which achieves the best de-icing effect? And this is what they want to look at, where they're going to look at 2 different ice regulation patterns and see how they affect aerodynamics. We'll get to that in a minute, though. Figure 3 shows the general cross-section shape of a wing leading edge with ice accretion on it. So you have the cutout of the leading edge, and the ice is just being built up on the front, and it really doesn't have much of a rhyme or reason in terms of its geometry. It's just quite random. It's jaggedy and rough. So that's not going to be good for an aircraft you can see immediately, unless you have a very small aircraft where perhaps turbulating the flow would be beneficial. But for human, like passenger aircraft, passenger airplanes at least, this is usually not good. You want to have a smooth surface to have as much of a laminar flow as possible to reduce drag. We don't need a turbulent flow to keep the throttle attached because the wings already keep the throttle attached during cruise a lot. For takeoff, though, that may be a benefit. I don't know. So in the figure 4 shows the aircraft wing scale, the model. So it looks very much like a hang glider wing. If you just think about a hang glider wing and then you take off like the person underneath, that's what it looks like. And you have flaps at the back. And the chord, the span is 371 millimeters. The chord they don't have here present, but they'll cover it later, at least the mean aerodynamic chord. Actually, I should mention the mean aerodynamic chord is different to the chord. The mean aerodynamic chord applies to when a wing has taper. So the chord at one point is not the same as another point. You want to find effectively the average chord of the wing over the entire span. That's what the mean aerodynamic chord is. And that's usually what we quote. So let's talk about the background aircraft wing scale model and simulated ice shapes. So they have a bunch of different aircraft with different ice being like built up on it. First of all, they have no ice whatsoever. Then they have the full ice leading edge, so along the entire leading edge. Then they have one called ice shape B and ice shape A. And we'll get into what the geometries are in a second. And they're simulated by 3D printing. So they're not actually real ice. They're just simulated these ice patterns through 3D printing them and stuck them on the leading edge, which is good enough. There may be some changes due to the ice in real life, perhaps making the air cooler as it goes over. However, the air should already be that cold anyway, so it shouldn't make too much of a difference. So they say D is the width of the single regulation ice. BA is the mean aerodynamic chord of the wing. And this paper defined the width of a single regulation ice as a dimensionless number called C. And this is the width of the ice divided by the mean aerodynamic chord of the wing. And this is really cool because when you try to non-dimensionalize things, it makes it so much easier to talk about the different effects. So they say the regulation ice A was set at the dimensionless ice size C of 0.15. So that means that the width of this ice is 15% of the mean aerodynamic chord. So it's fairly wide. The regulation ice B was set with a dimensionless ice size C of 0.2. So that means that the width of this ice is 20% of the mean aerodynamic chord. And in this experiment, simulation ice shapes were arranged in the leading edge of the wing model. So that's how they're characterizing these ice shapes here. And something to note is that the distance between these ice patches are the exact same as the width of the ice patches. So they're they're efficiently symmetrically placed along the leading edge, or uniformly placed, I should say. So let's move on to how they perform. They actually have a figure of the aircraft in the tunnel. It's just a regular model aircraft stuck in a tunnel. And they have 4 different ice situations investigated. They have no ice, regulation ice A, regulation ice B, and full ice, ranging from least amount of ice to most amount of ice in that order. So in figure 9, they say the maximum lift coefficient of the full ice state reduces by 53.4% and the stall angle reduces by 42.9% when compared with the no ice state. This is because ice accretion changes the aerodynamic shape of the wing surface. The flow field characteristics become worse, and this aerodynamic stability gradually deviates from the stable state. So there's a lot here. Let's unpack this. When you have the regular wing with no ice on there, the maximum lift coefficient occurs at about an angle of attack of 13 degrees about, and it's about 1.4. When you have full ice on the entire leading edge, the stall angle is 8 degrees. So it's horrendous. And the maximum lift coefficient is only about 0.8. So it's terrible again. As I said, reduces by 53.4% and 42.9% respectively, about halving both of these values effectively. Now, along with that, the drag obviously increases at this point as well. But even at low angles of attack, so pre-stall angles of attack, having ice along the entire leading edge increases the drag by about double. So it goes from about 0.15 to about 0. Actually more, it was about 0.5, so it's about triple the drag coefficient. Interestingly, when you put on just a little bit of ice, so ice regulation A, still the stall angle drops from about 13 degrees when you have no ice at all to about 10 degrees. And the lift coefficient drops by about 40% or 30%. When you have ice regulation, oh no, sorry, that was for ice regulation A. Ice regulation B, you get that, and then ice regulation A, it's not as bad because there's not as much ice. So you get a reduction in the stall angle attack by about 2 degrees, and the lift coefficient drops by about 0.1, so about 10%. So what this is showing is compared to no ice at all, any ice is bad for the aerodynamics of this aircraft that they've tested. But if you were to choose between having ice along the entire leading edge and having ice only along certain parts, this shows that you definitely have ice along only certain parts. This is far beneficial for the stall angle attack and the maximum lift coefficient, and also the drag. But one thing I want to point out here, which brings me back to the functional device called tubercles, is remember how I mentioned that tubercles are very beneficial for stall, how they make stall softer. So stall usually happens very abruptly. So often a wing will stall and then it will experience a massive reduction in lift very suddenly over a very short range of angles of attack. However, with tubercles, this is extended, so you don't get nearly as great a drop or as a severe drop. And this is what we're seeing here when we put ice onto the leading edge. The more ice there is, or like not the entire leading edge, but if you just put a bit more ice on the leading edge compared to none, then you'll get a gradual reduction in the lift coefficient. So the stall has been tempered a little bit, which is very reminiscent of tubercles again. So this shows me again that tubercles are very closely related to this geometry, and that makes sense to me. So we can conclude that any ice is bad for low angle attack aerodynamics, but during the stall stage, you can argue that having some ice is actually good. That's how the drag polar curves, which plot the drag coefficient compared to the lift coefficient. And this is a good way of measuring the aerodynamic efficiency of a wing or any object really. And the way that you do this is you look at how steep the slope is. The steeper the slope is, the more aerodynamic the object is in terms of lift production. And again, we see a similar sort of pattern here where if there's no ice, this has the best efficiency. When it's completely iced over on the leading edge, then that's the worst efficiency. And then the other two ice characteristics, two ice geometries fall between these two states here. And depending on how much, the more ice there is, the less efficient the wing is at low angles of attack, which makes sense. So those are general static situations. Let's look at the dynamic characteristics. The reason why dynamic characteristics are important is because an aircraft is not always static. If you have perturbations, they're dynamic and the aircraft will respond, and you want it to be stable. So let's look at the analysis of dynamic stability characteristics. So under a disturbance of a change in angle of attack of 1.5 degrees, so let's say there's a gust or the pilot accidentally knocks something or whatever. There's a 1.5 degree change in angle of attack. The flight state parameters have a dynamic oscillation process. Under the full ice state, the angle of attack under this perturbation increases sharply. It goes up to 9.5 degrees initially, which is close to the stall angle attack under full ice state. So what this means is, if you have the entire leading edge iced over, okay, you're going to get bad lift and drag reductions. But this is even worse because now, if you have a perturbation of only 1.5 degrees, which is not a lot, that's going to push the wing to 9.5-degree angle attack, which is now reaching the stall angle for this state, this full ice state, which means you could potentially lose the entire lift over the wing or much of it and start to become unstable. That's bad. So we can say here that the full ice state is very bad. However, compared with the full ice state, the peak values of the initial angle attack when you have the A and B ice shapes are reduced by 31.2% and 11.2% respectively. So in other words, you get the same perturbation of 1.5 degrees. And if you have ice state A, okay, the angle attack will still increase, but it'll only increase up to about 6 degrees instead of 9.5 degrees. What's more, that's well shy of the angle attack required for stall for this ice shape. For ice shape B, the angle attack will increase to about 9 degrees or 8.5 degrees, which again is not great, but it's not nearly close enough to the stall angle attack for this configuration to be an issue in that sense. The angle attacks then converge back to steady state faster, which is important. So you not only want to avoid the aircraft becoming completely unstable, you also want it to get back to the steady state of that it was to initially begin with faster. So under full ice state, the pitching angular rate, Q, which is how quickly this thing is going to rotate back, converges back to steady state at 10 seconds. Under ice shapes of A and B, the pitching angular rate Q converges back to the steady state at 5 seconds and 8 seconds, which is a reduction of 50% and 20% compared to the full ice states. So they don't go through the no ice on the leading edge. However, we can sort of probably assume that that's going to be the best situation, so it's going to be the most stable. But still, having these plasma generators de-icing some of the leading edge, we can dramatically increase the dynamic stability of the aircraft, which is good as well. So this shows that de-icing to some extent is very beneficial, even a little bit. So in conclusion, by ice shape regulation, the lift and pitching moment coefficients increase and the drag coefficient decreases compared to the full ice state. So it's very beneficial, but compared to the no ice state, it's not that good. Especially under the maximum lift coefficient configuration, the de-icing increases the stall angle attack by 4 degrees compared to the completely iced over leading edge. And that's very good. The aerodynamic characteristics of the aircraft were improved. Now, looking at the dynamic stability of the aircraft, a disturbance of 1.5 degrees was investigated, and under the full ice state, the angle attack increased sharply, and the initial response peak was 9.5 degrees, which is very close to the stall angle attack anyway, which is really bad news. However, when you have de-icing to some extent, the maximum angle attack that it will pitch to with this perturbation of 1.5 degrees initially decreases by 31.2% and 11% for the A and B ice shapes. So much better. So overall, we can conclude that de-icing, especially by plasma generators, is quite beneficial for safety of the aircraft, not only performance, but safety as well. So that's in this podcast. Make sure to let me know what you think about it. Put your comments in the section below, and make sure to like, subscribe, and also check out our other podcasts. And if you want to make your experiments 2 to 4% more accurate, and you want to make your CFD validation that accurate as well, then check out Atmosphere Hawk. It's just what we make to make your experiments and CFD more accurate. Link in the description. And if you want to get better at CFD and theory, like this, what we're doing here, then check out our courses. We also do them on our website. Link in the description. And see you in this podcast. Peace out, amigos.